Right, so having calculated all the raw data that we needed, so I've got values for length, I've made sure that they're in the right units, so they're in meters, I've calculated values for t squared, and I've made sure that they're in seconds, well, seconds squared anyway. I've already done the groundwork, so I know that that's what I need in order to plot my graph, get my straight line, and do the final bit of analysis to find g. So the other bit of processing I've just done then is to calculate the errors in all of those things, because when I plot my graph, I don't just need the points, I need the errors in the positions of those points. So I need the errors in t squared, and I need the errors in the length values as well. Now the errors in t squared are all different because they're all calculated, but length was actually a bit of raw data, so the errors in length are all the same. Now, in fairness, it doesn't show up very well in the video, but you should have the document in front of you so you can have a really close look at it. What you'll notice is that on the t squared axis, which I've put on the y axis, I have plotted the values. It's labelled as t squared. I haven't said what that is because it's quite clear all the way through the document what t and therefore what t squared is. But I have put the right unit of seconds squared. I've used as much of the graph as possible, so I haven't started at 0, 0 and then plotted all the graph up the top. I've condensed the axes down to make it as big as possible. Any gradients I calculate now will be a little bit better as a result of that. You'll also notice that I've put an error bar in the y direction. So every one of those values of t squared has its own plus or minus, and that's been turned into an error bar. They are quite tiny, but they're visible. They're more than a square, so I've plotted them on. What you'll notice on the length axis is, again, it's in meters, but this time I've put the plus or minus from the results table directly onto the axis. The problem with this is that it was plus or minus 0.2, and it wasn't really big enough to show up on the scale of the graph. So you wouldn't really be able to see an error bar. So what I've done there is I've put it on the x-axis to show that the errors are still valid, but it was too small to show as an error bar on the graph. In an ideal world, you'd have an x and a y error bar, but more often than not, one of them, or sometimes even both of them, are too small to show up. Just as a little aside, if I had calculated the errors in t squared and they'd been too small, which I mean they almost are, to be visible on the graph, but they were all different, what I would do is I'd do like I've done with the length one. I'd put a plus or minus as part of the label on the y-axis, and I'd just pick the worst, the biggest error of all the ones that I'd calculated, and that would be my plus or minus. Provided I haven't got some sort of anomaly where one of the errors was absolutely enormous, in which case I might discount that. Or if they were quite big, I could perhaps take an average. To be honest, as long as you deal with it and you can justify why you've dealt with it, or dealt with it in that way, then it's acceptable. You just need to make sure that you take the errors into account for both axes on the graph. Alright, other little things to look for then are line of best fit. Don't do daft things like make it go through the origin. It would be even more pointless on this one because the origin is not the bottom left corner of that graph. The origin is off the graph. Fit it to the points, not to where you think it should go. Even if you think it should come from the origin, if it doesn't look like it's going to, don't force it to, otherwise what was the point of collecting any of the data? If you've got a bit of scatter, make sure that you've got as many points above as below the line, and it follows the trend of the points as best as it can. If you end up with something that's curved when you know it shouldn't be, put a curved line of best fit on. But if you need a straight line of best fit to do the final bit of analysis, put that on as well and annotate the graph. Say that you've done both, say why. In reality, you would go back and start looking at the experiment again, but for the sake of an assessment, you need to be able to demonstrate that you can take the gradient of a graph and use it to analyse something. If you don't have a gradient of a graph because it's a curve, well, then you need to put one on it just so you can demonstrate that point. But you don't want to come off as if you thought it was a straight line when it's blatantly a curve. That's why I say do both and annotate it. And then all will happen is I'll read it and go, oh, you clearly saw this was a straight line, but that was a curve, but you've drawn the straight line on it so you can do the next bit, but you've put the curved line of best fit on as well. I absolutely understand. Some of the experiments you do will be really, really good like this one. Very close to the line of best fit, really good straight trend. You can see that second to last point up the top right-hand corner is a bit of an outlier. It's not remotely an anomaly. But while the others are quite close to the trend. Some of the results that you get in some of the experiments that you do will be all over the place. It is the nature of the experiment that you're doing. So don't take it the wrong way if it's not, but do just double check that you've calculated your values correctly. If anything weird does happen, like you get curves or a lot of scatter, go back to your raw data. If your raw data's all over the place as well, and you kind of know why it was, then that's just part of the experiment. Don't worry about it. But if there's steps or anything strange in your data, just double check you've converted things correctly. You've not left, for example, time in minutes and seconds when you should have converted it all into seconds and silly things like that. Just double check that you've done everything and it's all in the right units. The only other thing then this would need to do is be attached into your lab diary, and it would need to be labelled as graph 1, and it would need to have a bit of a caption. You'll notice I haven't put a title on it here. This is just the sort of intermediate stage. There's 2 graphs in the document that you're looking at, and the reason for that is we're going to come back to this graph, and we need to draw something else on it, but I didn't want that to confuse the initial drawing of the graph. So we'll come back to this in another part in a moment or two. I am actually just jumping ahead to the next part, but I just put a few notes on the next part that is to do with plotting the graph. So do just make sure you have a little look at these. And this is a list of things that your graph needs to entail. But I'll go on to the actual next part in a separate recording.